Hi everyone. In this video, we're going to focus on nucleophilic addition. This video would serve as an introduction to the reactions of carbonyl compounds. So the reactions of carbonyl compounds are called nucleophilic additions. And this is because of the structure of a carbonyl group. Okay, so reactions of carbonyl compounds. Like I said, this is sort of dictated by the structure of the carbonyl group, the electronics of the carbonyl group. So if I were to use a general structure for a carbonyl compound, let's say that we're going to represent the carbonyl compound as RC double bond O R prime. Okay, so I'm differentiating the two R's here. Now, I'm going to further qualify it as if R prime equals H, then we are looking at an aldehyde, and when R prime equals R, then we are looking at a ketone. So you can basically use this general structure to represent both aldehydes and ketones. So as far as carbonyl compounds are concerned, both aldehydes and ketones, these behave as electrophiles. In reactions. And this is attributed to the presence of this carbonyl carbon. Okay, so this carbon here, that's the carbonyl carbon. And this carbonyl carbon, sorry, let me write that out again, a little bit more legible. Okay, let me do this. So behaves as an electrophile, and the reason for this is the carbonyl carbon. This carbonyl carbon is connected to this double bonded oxygen, which means we can now write a resonance form where we push off that pi bond to that oxygen such that the oxygen gets a negative charge and the carbonyl carbon gets a positive charge. So you can notice that this carbonyl carbon is electrophilic. So now in that resonance form, it has a formal positive charge on it. But even if that's not the case, in the other resonance form, the first resonance form, there is a del positive, a partial positive charge on the carbon and a partial negative charge on the oxygen because of the inductive effect of the oxygen. The oxygen is more electronegative than the carbon. So in either case, this carbonyl carbon, it serves as what we will call the electrophilic site in the molecule. Okay, that is the electrophilic site. That means it's the electron deficient site. So since it is an electrophilic site, what that means is a nucleophile can attack this carbon. So a nucleophile can come and attack this carbon. Now let's look at what does that attack look like. Now, another thing to remember here before we go into that discussion is that this carbonyl carbon is sp2 hybridized, which means the geometry around that carbon is trigonal planar. Okay, it's trigonal planar in nature. So when we have a carbonyl compound You have the double bonded oxygen. I'm going to put the R group on a wedge and the R dash or the R prime on a dash to say that we are looking at a trigonal planar structure. Okay, so this is sp2 hybridized. So the geometry around that carbon is trigonal planar. So when a nucleophile comes and attacks, or when we have a nucleophile, important thing to remember here is that any nucleophile, and actually, I think let me give me a little bit of a three-dimensional perspective here. So the way I'm looking at this molecule right now, the carbonyl compound, is that the double bonded oxygen is in the plane of the whiteboard. So it's in the plane of the whiteboard. The R group on the wedge is coming out of the plane of the whiteboard, straight out, and the R prime is going straight inside. So the molecule at this time is oriented orthogonal. So if this is the carbonyl carbon with the R groups on it, the molecule is oriented orthogonal or perpendicular to the plane of the whiteboard itself. Okay, so at this point, the nucleophile, any nucleophile, because this carbon is partially positive and the oxygen is partially negative, the nucleophile has two options at this point. It can attack the molecule from the top face. Okay, so this is from the top face, or it could go and attack this carbon from the bottom face. And both of these attacks are equally probable. Okay, and which doesn't matter which one happens, the double bonded the carbon-oxygen pi bond is going to open up and go to the oxygen atom. So both attacks are equally probable. So what that means is whenever there is a possibility for a chiral center to form, you will get a racemic mixture under these conditions. Okay, so when the attack happens now, and we will consider, let's say, the attack from the top face, or we can consider both attacks here. So let's just consider both attacks. So what's going to happen is, if the nucleophile attacks from the top face, then we will have that carbon here. We don't have to show the carbon, but we'll have the oxygen with the negative charge on it. The nucleophile came and attacked from the top face. So I've drawn it on a straight line from the top. The R prime that was on a wedge is still going to be on a wedge, but it's going to be pointing down now. And the R prime would still be on a dash and it will be pointing down. That's one possibility. So the addition or the attack, the nucleophilic attack has happened. If the attack happens from the bottom face, what we will get is oxygen with a negative charge. Since the nucleophile attacks from the bottom face, we will get nucleophile here. Okay. So this is the attack from the top face. This is the structure for the attack from the bottom face. The nucleophile attacks from here, and now the R group is still going to be on a wedge. R prime is still going to be on a dash, but pointing up. So you notice how what you made here are enantiomers of each other. Okay, these are enantiomers of each other. So the chirality is built in, and you always make a racemic mixture. So you're going to make equal amounts of both of these enantiomers. Okay, so that's something very important about attack on a carbonyl carbon. Now, in most cases like this, when a nucleophile goes and attacks the carbonyl carbon and opens up the pi bond, the final step here is a protonation event. Okay, so you could add water and the oxygen would get protonated. Electrons would go to that, the oxygen would pick up the proton. Electrons from that bond would go to the oxygen atom here. And the same applies to for this oxygen that can get protonated. So essentially what you get in the end is you get a molecule where the nucleophile is connected to that carbon, the oxygen has added a hydrogen to it, and you will get R prime plus its enantiomer. You're going to get that. And these reactions are done stepwise. So this is the first step, and this here is the second step. So you do it in steps, one by one. You do not put them simultaneously. Now, in some cases, it is okay to mix your nucleophile with your solvent or with water, but it may not work in every case. Okay. Now, the other thing to mention here is when the nucleophile attacks, notice the change in hybridization. That carbon is now sp3 hybridized. That's why we have the chiral center. So to start off, the carbonyl carbon is sp2 hybridized, but in the product or in the intermediate that leads to the product, that carbon is sp3 hybridized, and it continues to be sp3 hybridized in your product. So the reason why it's called, this process is called a nucleophilic addition, is that there is an attack of the nucleophile initially. That is your rate limiting step. And then a final protonation. So when you compare your starting material to the product, what you've done is you've added something to the carbonyl bond, okay, the carbon-oxygen double bond. So there was a double bond between the carbon and the oxygen. In the product, there's only a single bond between the carbon and the oxygen. You add the nucleophile to the carbonyl carbon, or what was the carbonyl carbon, and you protonate that oxygen. So you've added something to that double bond. So that's why it's called a nucleophilic addition. And it is initiated by that nucleophilic attack on the carbonyl carbon. Now, this is one of the possible mechanisms, actually. And we'll look at some of this in detail later. But let's go into another aspect of the reactivity of carbonyl compounds. Okay, so we have two carbonyl compounds, aldehydes and ketones. So one important question that we need to answer here is, are aldehydes and ketones equally reactive? Okay, that means, is the reactivity the same for both of them? And the answer to this is a big no. We will understand why. So if we compare an aldehyde to a ketone now, again, for both of them, we can write resonance forms for both of them. So we can write a resonance form for the aldehyde, and we can write a resonance form for the ketone. Okay, and just by looking at the initial structures as well as the resonance forms, we can tell, or we can rationalize which one of them is going to be more reactive. And there are two reasons for why one would be more reactive than the other. And again, I would like to give you the answer first. The answer is that aldehydes are more reactive than ketones, generally speaking. Okay, so aldehydes are more reactive than ketones. Why would that be? Okay, why would it be so? So, like we just discussed, the reaction here is a nucleophilic attack. So you can cite two reasons for this. One is a steric effect. okay, which means this relates to crowding in space. So since the attack on these carbonyl compounds, okay, involves a nucleophile attacking that carbonyl carbon, and then that pi bond opening up, and similarly here, the nucleophile attacking the carbonyl carbon and the pi bond opening up, since that's the first step in the mechanism, okay, or at least that's the rate limiting step in the mechanism, the sterics around this carbonyl carbon, those would matter. And so if you look at the carbonyl carbon in case of an aldehyde, it has an R group on one side and a hydrogen on the other side. Whereas the carbonyl carbon in case of a ketone has an R group on both sides. So based on steric effects, okay, the carbonyl carbon is more crowded. Okay, or I guess a better way to phrase this would be there is more crowding around the carbonyl carbon in a ketone, which makes it less reactive. So if there are two carbonyl compounds, one is an aldehyde, one is a ketone, and if we have one nucleophile, the nucleophile would find it easier to go and attack the aldehyde compared to the ketone. So the aldehyde is going to be more reactive here, okay, because that reactions does not have any steric associated, or it has less sterics associated with it. So steric effects is one reason why an aldehyde is more reactive than a ketone. The second effect is an electronic effect. Okay, it's an electronic effect. And this comes down to the charge on the carbonyl carbon, or what is the carbonyl carbon. So as we see between the aldehyde and the ketone, they both have a partial positive charge on that carbon atom, on the carbonyl carbon, or if we write a resonance form, they both have positive charges, a formal positive charge on that carbon atom. Now, again, the difference is the carbonyl carbon in the aldehyde is connected to one R group or one carbon containing group, alkyl group, whereas the carbonyl carbon in a ketone is connected to two alkyl groups. And recollect that alkyl groups are electron donating in nature, okay? They tend to push electron density towards positive charge. Okay, so they have a plus I effect. They donate electron density. And so since the carbonyl carbon in an aldehyde is connected to only one R group, it is getting some electron density from this alkyl group. But the carbonyl carbon in the ketone is getting electron density from two R groups. So could be twice as much if they're both equal or if they're both identical. Okay, so that diminishes the electrophilic nature or the electrophilic character of the carbonyl carbon. Okay, so alkyl groups are electron donating in nature, and what this does is it diminishes these the electrophilic character of the carbonyl carbon. So because of those two reasons, okay, one, a steric effect, and second, an electronic effect, an aldehyde is more reactive than a ketone in these nucleophilic addition reactions. So the presence of these two alkyl groups or carbon-containing groups makes the attack difficult. One thing, that's the steric effect, okay, because there's crowding around that carbon. The second is an electronic effect where the presence of these two alkyl groups, they diminish the positive charge or the electrophilic nature of that carbonyl carbon. And so when these are combined, they both work in favor of the aldehydes. So the aldehydes turn out to be more reactive than their ketone counterparts. So that was an overview of the nucleophilic addition reaction. In the next video, we're going to go back, review some of this content, but also look at nucleophilic addition under strongly basic or nucleophilic conditions versus acidic conditions. How is the mechanism different depending on the reaction condition? Okay, bye.